Welcome you to today's lecture. Today we will continue from the Laplace transform. We discuss how to calculate the Laplace of a differential. So let's do an example here. So for example, I want to solve a differential equation using Laplace. So for example, if I want to take the Laplace of differential equation of this one, which is of a second order. Okay. So let's see how we solve this problem using Laplace transform. So if I take the Laplace on both sides, so if I apply the formula for the second from this equation, which is given to us here, so if I take the Laplace of y double dot, it becomes s square y of s, then minus s y of 0 and minus y dot of 0. So this is for first term, this one. Okay. Similarly, put plus sign here, a1, and take the derivative of y dot. Take the Laplace of y dot, it becomes s y of s minus y of 0. Similarly, plus a2 y of s is equal to b u of s. So this is what we, so if we rewrite this whole equation, so it becomes s square y of s plus a1 s y of s. Similarly, plus a2 y of s is equal to b u of s plus s y of 0 plus y dot of 0. Similarly, plus a1 y of 0. So this is what we get. Now we have to plug in the initial conditions. So assume initial conditions equal to 0. So in that case, it becomes s square y of s plus a1 s y of s plus a2 y of s equal to b u of s. So if I just take out y of s, it becomes s square plus a1 s plus a2, and is equal to b u of s. Now if I take the ratio of output to input, it becomes b divided by s square plus a1s plus a2. So as we define this ratio as a transfer function, this definition only holds if your initial conditions are 0. So this is the way you can solve a differential equation and also find the transfer function. So in other words, we know that we have input here u of s and we have output here y of s, and this is the transfer function here, s square plus a1s plus a2. So transfer function we normally represented at g of s, that is equal to b divided by s square plus a1s plus a2. It's the transfer function. So if we look at actually what we did here is we take the Laplace of convolution of g of t, it is equal to u s g of s. So this is the way we can use Laplace to find out solution of the differential equations. And now let me so what we did here actually, we consider an input to a system, input to a plant actually. So This is our plant, and we get some output y of t here. Okay, so this plant in frequency domain we represent it in terms of transfer function. Now let's solve another example here. So this is another example where we have a model, dynamic model actually, which has a mass with a damper, and mass is m, damper is b, force is applying here. This is the way displacement is done. When we want to write the equation in terms of velocity, so it becomes m dot plus bv equal to f. So this is the equation. Now when we apply and we consider initial condition is 0, so in that case we can calculate the transfer function between velocity and force, applying the Laplace on both sides. So Laplace mv dot plus bv is equal to Laplace of f. So it's easily written as when I apply the Laplace, so it becomes, because there is only single derivative, it becomes ms v of s. Okay, also minus initial condition, that is m times v of 0, again b v of s equal to f of s. So here the main idea is, as we know that initial condition is 0, so I can rewrite this as ms v of s plus b v of s equal to f of s. So if I take out v of s common, so it becomes ms plus b times v of s equal to f of s. So as we know that the ratio of output to input is transfer function, so in that case g of s equal to f of s divided by v of s, which is equal to 1 divided by ms plus b. Now assume that this is the transfer function we calculated. Now let's see how this transfer function help us. If I go to next one, so I just wrote transfer function here. It becomes 1 divided by ms plus b. Now how this transfer function help us? So let's see, assume that you want to calculate the velocity let me correct it because I just do a bit wrong here. I need to, this is not, let me correct it because this is the ratio of output, that is v of s, input is f of s. Okay. Similarly, I need to correct on the next page. So this is v of s, f of s. Okay. Now let's see if I want to find out the output to a particular input to the system. So I have to plug in the input here to calculate the output. Now let's assume that we are giving a step input to the system. Assume that we are giving step input to the system. Now let's see how output behaves. So if we look at the table, before looking at the table, let's plug in the table. We know that Laplace is 1 over s. So if we plug in here, it becomes y of s equal to 1 divided by ms plus b times 1 over s, because this is the Laplace of step input. So if we look at the in the Laplace table, and if we look at the property number 11 there, it says that if you have some variable written as a divided by s into s plus a, its inverse Laplace is 1 minus exponential minus a t. Now to compare these two, we can calculate the result here. Only what we have to do here, we have to plug in the b here. Now we assume with the input f naught, so we have to write f naught here as well. So to form this, to apply this property, we have to rearrange our v of s as we need b on the top, so it becomes b divided by s into, take the m out, so it becomes, because s is common there, so take the m out, so it becomes s plus b by m. So take that m on the top, so you have same these two, as here you have a on the top, you have the same a. Okay, so this is the similar to this one, and then multiply by f naught. So when we apply, because we are adding another b here, we need to divide it so that our equations remain the same. When we apply the inverse Laplace, so it becomes y of t equal to f naught divided by b times 1 minus exponential minus b by n t. So this is the same result that we calculate when we solve directly the differential equation to find the step response of this system. So this Laplace actually help us to find out these solutions. Okay, ji. Let's see if we have initial conditions and how we solve the problem. What about non-zero initial conditions, or initial conditions that are not equal to 0? Let's see if we consider the same problem, that is mv dot plus b and is equal to, because we are interested here to look at what is the initial condition solution of this differential equation, and we put input to the system is 0. In that case, so if we apply the Laplace on both sides, so Laplace on both sides, it becomes ms v of s minus m v of 0 plus b v of s is equal to 0. So when we do a little manipulation here, so it becomes m plus b times v of s, and take the initial condition on the other side, it becomes m v naught of 0. So v of s in that case is equal to m divided by ms plus b times v naught of 0. So this is the initial condition response. So actually you look at this one, this is the same, so this tells you about the modes of the system. So modes mean that these are actual dynamics that exist within a system. Now let's so this mode actually input here, this tells you how much mode is included to develop the response of the system. Now if I look at the time response here, so for example, if I take the inverse response of this, so f s is equal to m of 0, ms plus b. So if we apply the inverse Laplace here, if we look at the 7 number on the table, entry is that says that when Laplace is 1 over s is equal to exponential minus at. Now look here, so when we apply here, y of t becomes v naught times exponential minus b by mt. So this is the initial condition response of the system. So you can use Laplace to find out the initial condition response. So here what we do here in Laplace, actually we can find out the transfer function. Transfer function plus initial response. So initial condition response. So for transfer function, actually we get, and we can solve it using the inverse Laplace transform. So that gave us, from the transfer function, gave us g of s. So it is important to note that in that case initial condition is 0. Now when we do the inverse Laplace, then we can calculate the impulse response of the system. So in other words, inverse Laplace of y of s actually equal to, is defined as y of t, that is calculated after solving this formula, which is 2 pi j sigma minus j infinity, okay, and plus j infinity y of s exponential s of t ds. So this what we can do. So this is only used to prove things. Otherwise we use the Laplace table that help us to solve the problem, the related problem. Now we move to next one. So here as we know that if this is 1 over s, so this means that we are talking about step input, okay. In inverse case, similarly 1 over s is equal to exponential minus at. Similarly if it is a divided by s square plus a square, this is equal to something cos of at. So these are few properties that normally we required. So, or we always refer to table to solve a problem. For example, if we have an output given to us as 9s square plus 16 divided by s into s square plus 4, and we have to find y of t. Now how we do that? Because this type of relation is not available in the table, so what we have to do, we do some mathematical manipulation so that we transform it to the required property and solve it. So how we do that? As you know that this is partial fraction, and we can solve it using partial fractions. How we do that? We just write this one, 9s square plus 16 s into s square plus 4 y of s as equal to, we take the roots here. So for single root we just assume constant on the top. For second order we assume the first order polynomial that use a different parameter, for example bs plus c whole divided by s square plus 4. So now here we have to find these unknown terms. These are unknown terms. So we use partial fraction techniques to do that. So how we do that? We just do the cross multiplication and we get the result. So when we do the cross multiplication on both sides, so what happened on the right side becomes s square plus 16. When we do the cross multiplication is equal to a times s square plus 4, then plus bs plus c times s. So this is the way we can write equation here. Now for this equation we can use this equation to solve the problem. There are different ways. If we do the comparing coefficients of s square, say s power 0. So for s square it becomes 9a. So directly you calculate the value of a. Similarly, a plus b. Sorry about that. Because when I multiply with it becomes b. So this is equation number 1. Now when you compare with s, so there is no term with s, so coefficient is 0 here. There is no term with a here, so again there is only c. So in that case c is directly calculated as 0. This is equation number 2. Now for third one, if we consider the constant, so on the left hand side we have 16, on the right hand side we have 4a. So from here we easily calculate a as 4. Now if we put this 4 in equation 1, so from here b becomes 5. So this is the way we calculate the partial fraction. When we do that, y of s becomes 9s square plus 16 divided by s into s square plus 4 becomes 4 divided by s plus 5s divided by s square plus 4. So now it's easy to apply the inverse Laplace, so it becomes y of t 4 exponential u of t, because 1 over s is just u of t. Okay. U of t means that you are multiplying with step input. Similarly, for that case it becomes 5 cos of 2t. So this is the solution we can calculate using Laplace transform. So let me stop here.